to our undergraduate research symposium. This is going to be presentations from our summer undergraduate research students. Just to let you know that we had 15 students in the program this summer, which is 2 or 3 times what we typically have at least. So very happy about that. I also wanted to mention that 2 people are not mentioned in this program, which actually did most of the work, and that was Rachel Merritt and Brendan Cross. And what they did, among many things, was lead a weekly seminar teaching these students how to make presentations. There were things about how to write papers, ethics, I believe, how to present yourself, etc. So again, they deserve most of the credit here. So we appreciate that very much. So I'm going to turn this over to Rachel, and she's going to be introducing our speakers for today.
All right, well, thank you everybody for being here. I know that this is a terrible time of year for scheduling anything, so I'm so happy that so many of you were able to come out and support the students. And I also just want to say thank you to the students for listening to me talk for an hour a week for 8 weeks and still showing up every week. I was very impressed, and they've all done very hard work, and I'm very proud of all of them and very excited to see what they have to present today. So to start, we are starting with one of our 2 Raghavan Fellows, and that is Kara.
Is it on? Did you turn it on?
I just turned it on.
Okay. It's the end. That's it.
Clicked through it.
Over.
That's done.
Thank you for coming.
Good talk.
Okay. Good afternoon, everyone. So like Rachel said, I'm Kara Gartner. So I was working with Dr. Jane Pratt, and I'll be talking about the research that I did on convective penetration during the red giant branch luminosity bump. So first of all, what's convection and convective overshooting? So this visualization here is a velocity magnitude diagram. So you can see that the velocities are higher in this convection zone. So in solar-like stars, there's a convection zone over a radiative zone. And since stars are heated internally, in this convection zone, the hot plasma is rising. It's getting up to the top, it's cooling down and sinking back down to this boundary. And at that boundary is where convective overshooting is happening. So convective overshooting is when material from the convection zone is carried into that stable radiative region. It's important for stellar evolution. It causes mixing, it enhances diffusion, it's changing the composition of the star. So it changes the stellar interior by exciting internal gravity waves that happen in this radiative zone. And it can change which regions of the star are actually convecting by changing temperature and density gradients. So the red giant branch and luminosity bump. What's the red giant branch? It's a later stage of evolution for low and intermediate mass stars, so it happens after the main sequence. The stars in the red giant branch are more luminous than the stars on the main sequence. Some interesting things about the red giant branch are the first dredge up, which is when the convection zone becomes deeper and mixes fusion products that were in the interior up closer to the surface, which changes the composition of the outside of the star. And the luminosity bump, which is when the surface luminosity drops on the HR diagram before continuing to rise again. So why did we do our simulations in the luminosity bump? The luminosity bump has a deeper convection zone and a higher luminosity. So the higher energy in the convection zone makes it easier to model. And in this phase, so in the red giant branch, in the luminosity bump, there's different abundances of lithium and carbon and other elements that make the models not match up with observations. So extra deep mixing is needed to better match the models with the observations. And the simplest extra deep mixing that we can model is overshooting, which is what we did. Some other examples would be meridional circulation and internal gravity waves. So the actual research. So why are we performing a computational study? So you can't directly observe the stellar interior. You can do astroseismology, but it's a relatively new field. And simulations give us more detailed data than observations. So what I did is I ran 1D stellar models using the MESA code, which is the Modules for Experiments in Stellar Astrophysics. And then I ran 2D and 3D time-dependent hydrodynamic music models. And music is the multidimensional stellar implicit code. And then after we did all that, I ran statistical analysis. So what we were looking for is, does convective overshooting change with stellar evolution? So we would expect that overshooting would change with parameters like convective velocities or the size of the convection zone. Most people model with a constant overshooting length with respect to the pressure scale height, and they do it with an average. So we're not doing either of those things. The model that we're using is this extreme value theory from this paper by Dr. Pratt, and we're not using an average. So you can see here on this bottom axis is the degree of the star. On this axis over here on the right is the penetration depth with respect to the radius, and on the other side, or on that axis, is the penetration depth with respect to the pressure scale height. So these red plumes that you can see are the overshooting plumes. This black line at the top is the bottom of the convective boundary, and this dotted dashed line right here is the average. So if you take the average, you miss all the important stuff that's down here. And that's why we're using this other model to model overshooting. So the actual simulations. So I ran in MESA, I ran a 3 solar mass star with solar metallicity. And then we took 6 of those profiles that were in the red giant branch on the luminosity bump. And we ran them in music and created 6 hydrodynamic simulations. So the simulations in music use the MESA equation of state and opacity tables. So the simulations go up to helium burning, but they don't include helium burning. And you can see here, so these are radial velocity diagrams, and you can see that the convection zone is larger in this model, which is the oldest model, than it is in, the convection zone is smaller in this model, which is the oldest model, than it is in the youngest model, which is all the way on that side. So the HR diagram, I think so a lot of you are familiar with this, is so the log of the effective temperature is on this x-axis, and on the y-axis is the log of the luminosity. So these dots up here are the different profiles. So the youngest profile is actually this one at the top here, and the oldest profile is the one at the bottom. If you look kind of closely, you can see that this actually separates from this line, and that's the luminosity bump. So the luminosity in these models is decreasing instead of increasing as they age. So, and then the results. So, like I said before, convective overshooting is expected to change with different quantities like the size of the convection zone or the convective velocities. So this is a plot of the convective velocities. So on this axis we have the radius, and on the y-axis is the root mean square of the velocity. And these dotted lines here, which correspond to the colors that each of these lines are, is the bottom of the convection zone for that simulation. So you can see that the convective velocities for all of these stars are different. This one in particular is much higher. And then we plotted the overshooting. So on this axis is the age, and on the y-axis is the overshooting with respect to the pressure scale height. So that top line is overshooting calculated with the kinetic energy flux, and on these orange dots are the overshooting calculated with respect to the heat flux. So you can see that the overshooting length is changing. It's not a constant like a lot of people model it. And it's ranging between 0.2 and 0.5 of the pressure scale height. So right now there's not a clear trend. These are lower resolution models, and we still have some more analysis to do to figure out what's going on in some of these middle ones. But for future work, we would want to know, is age the only factor? We would do more simulations with different stars at higher resolution. So I've actually already run in MESA a 1.5 solar mass model, a 2 solar mass model, and a 5 solar mass model. We'd also want to do more metallicities because we only did solar metallicity, and metallicity would have a big impact on how the star is evolving. And then in collaboration with the team in Exeter, I'm going to be doing an analysis of internal gravity waves that I haven't started yet, but working on it. So thank you everyone for coming. I'd like to acknowledge the Undergraduate Research Committee and Dr. Raghavan for the Raghavan Fellowship. And that's all I have today. So.
Do you have any questions for Kara?
So observation
observationally, what's going to be the easiest way to see if you're wet?
It's a good question. I don't necessarily know if I can answer that with certainty.
Well, you showed an HR diagram there.
Yeah.
You had an offset in luminosity.
Yeah.
But of course, astronomers don't measure luminosities. We don't
Right.
measure temperatures. We measure colors. We measure magnitudes. So I guess it's really, is there a particular magnitude, a particular distance measuring device that's up in space that might give us the data?
I'm honestly not sure.
The answer might be Gaia.
Okay. I'll have to ask about it.
Yes.
Yeah.
Ask Jane about
Her
Gaia.
advisor's not here.
Yeah. I'll have to ask.
So on your next plot, the one sort of showing, or I guess the next one after that, showing those results. So I'm just curious, is there random variations as a function of time here, or if you were to sample that a little more finely in time, could you map out how the kinetic flux and heat flux are changing with time? Or just wondering if those are sort of randomly varying with time.
Well, so we'll have to do more simulations, like more more ages, and we'd have to do higher resolution. So right now, we think that maybe there's no trend because something's going on with these right here in the middle. So we'd have to do more ages to figure out if it's changing with a trend. So.
Let's thank Kara again. And our next speaker is our second Ragavan Fellow, Francisco. Oh, and sorry, we have a multimedia exchange going on for each of our speakers. Good thing Gary had to do the award ceremony, so I'm a professional.
Hopefully there. Cool. All right, cool. All right, well, let's dive right in. So my name is Francisco Martinez. I've been working with Dr. Crenshaw and his AGN group this summer over measuring mass outflows for 2 other galaxies and also measuring obtaining constraints for the broad emission lines in some of these galaxies. And so in this talk, I'm going to take you all through the journey that we went through these past 8 weeks to do this. But first, we need to start with, these are basically the objectives that I had, getting the constraints for the broad component. And so obviously, we need to start with understanding what is an AGN. So an AGN, I'm sure a lot of you have seen this before, consists of this unified model where in the center here you have a supermassive black hole surrounded by a broad emission line, or broad line region, and then over on the outsides you have these narrow line regions. And so throughout the talk you might hear me say, you might have a Seyfert 1 galaxy or Seyfert 2. When we say you have a Seyfert 1 galaxy, it means you're an observer looking through all of this material. So you're going to be seeing narrow line region emission, broad line emission, and everything in between. For a Seyfert 2 observer, you're going to be looking at essentially everything minus the broad line region, because you can see that nowhere along this path do you get any of the emission from this center region. And to kind of drive the point home a little bit further, if you take a spectra of these 2 different types of systems, you can clearly see that in the orange for Seyfert 1, you're going to get emission and the continuum from the host galaxy. But you can clearly see that the emission lines compared to a Seyfert 2, some of these lines get very broad. And so when we mean we have broad emission, we literally mean that we have a very broad line, and narrow lines are simply these very narrow lines. So, and I highlighted these 2 regions in particular because they're going to be some of the 2 regions that we use to our advantage the most, because over here in the blue side of the spectrum, we have the strong O3 emission lines, and in the red, we have H alpha, a strong red line. So our observations consist of essentially using the Hubble Space Telescope. On board is the Space Telescope Imaging Spectrograph, or STIS for short. This spectrograph has a very narrow slit width, so that's going to allow us to get a very high spatial resolution to be able to see what the fuzzy clouds are doing in the center of these galaxies. However, you can only achieve somewhat of a moderate signal to noise because to get time on the Hubble Space Telescope is very competitive, and so you can't always look at an object for so long. But we can couple this with ground-based observations from Apache Point Observatory, and this is the instrument we use here. So the dual imaging spectrograph is what's on board there, and that has a 2 arcsecond slit width, so a lot larger. So that means we're going to unfortunately get lower signal to noise, a lower spatial resolution, but that'll give us, because we're on ground, a higher signal to noise to look at objects for a longer time. And so to start us off, so I was entrusted with calculating mass outflow rates for these 2 galaxies. Dr. Crenshaw and a previous grad student, Mitch Rowalski, as we all probably know, have been doing calculating mass outflows for 3 previous galaxies in the past, and so we wanted to increase our sample to 2 other ones. And so it's Markarian 3 and NGC 1068 to the right. And so to get us started, we need to we need to use the Hubble Space Telescope to zoom into this very inner region. And if you do that and obtain an O3 image, so an image just letting the O3 light in, you're going to get something that looks like this. And of course, in white, you see the slit that runs through the image. And so in order to do mass outflow calculations, you need to basically have 3 things. The first thing consists of photoionization models. These are going to be used in order to get a understanding of what the gas is doing in the center. You're also going to need 4959 and 5007 O3 images, like this one you're looking at over on the right. And we're also going to need a velocity law to be able to see how the gas is moving throughout the system. And throughout this talk, I'm just going to go through the steps that we used for Markarian 3, because the process is very identical to 1068. And so the very first beginning is we need to figure out how much mass is inside this slit. And so in order to do that, we basically use this equation over here on the left, where it basically depends on the column density. This is the mean mass per particle, which we assume to be solar abundant, the mass of a proton, and then the luminosity of the H beta over the flux of the modeled H beta values, which the green values come from the modeling. The luminosity from H beta is derived from the observations that we get along the slit. And again, because these photonization models, the way they were modeled essentially were the people considered they considered modeling both the redshifted gas, so gas that's moving away from us, and gas that's being blue shifted coming towards us. But within each of those kinematic components, you had both a high, medium, and low state of ionization that was calculated. And so a big part of this was just keeping track of everything. And so in a lot of my results, you'll see that I'll have a red curve and a blue curve. Those will be representing the red-shifted kinematic gas and the blue-shifted kinematic gas. And I basically go through and calculate the mass profile, mass outflows for individually for the blue and the red-shifted gas. And so this is one of the results here. So over here on the left, we have the mass as a function of distance. And this is calculating the entire mass along the slit that you saw. And if we compare this result over to the image from HST, you can see that a lot of these peaks do line up really nicely with these O3 knots that appear in the image. And so again, you can do this same process for 1068. And again, you find that very similar trend where you get certain peaks at certain points. And again, the blue is the individual mass contributing from the blue shifted component. The red curve is the mass contributing from the red shifted component. And the black is the sum of both of these. And so, great. So we've used the photoionization models to their fullest extent, basically. They help us get the mass along this slit. And now, how do we get the rest of the mass outside of this slit? And in order to do that, we use a calibrated O3 image. And what we do with this is basically overlay our bins, and then we'll program into the image these semi-annuli, where we can calculate how much flux falls within each of these annuli. And what we do is basically, if we know the mass inside one of these bins, and we know how much flux there is sort of around this whole radii, then we can carry that mass on through. And this image just shows the flux that you get from each of these cutouts as a function from the center. But when you have that piece of information, then you can use this relation here. Since we know the mass along the slit, we know how much flux was contributing, or we know the mass in the slit at each location. We know how much flux there is from each location, and we know how much flux there was outside of the annuli. Then we can use this relationship here above to calculate how much mass there is outside of the region. And this is what you find from Arcarian 3. And again, similar peaks to where they were before. And you could do the same thing for 1068. And so, great. So we're almost there. So the next part to our mass outflow quest is the velocity law. So in order to get the velocity law down right, we have to use the HST spectrum in order to see, we need to get radial velocities, and this is what they come out to be when you make an observation of the center. And we can fit it to a biconical outflow model. And within each bins that were modeled from the very beginning, we can extract the velocities across each bin. And within each of these bins, we can start to determine which are the blue and the red shifted components, average these guys all out together, and with those average velocities, then project them into the plane of the galaxy, and you arrive at something that looks like this, where around the center you have roughly almost equivalent to no velocity, but as you go further, a little further out, you reach your maximum and then gradually drop off. And this is important because, again, in the modeling, there was red-shifted gas and blue-shifted gas, each individually who had their own masses contributing to all this. And so when you assign all that together and piece it all together, you arrive at this mass outflow result, where the mass outflow basically goes as the mass inside of that entire annuli, and multiplied by the velocity that we got before, divided by the extraction radius. And over here on the y-axis, you're looking at how much mass there is leaving as a function of solar masses per year over distance. And you could do the same thing for 1068. And so we got through that. And so the second part of the summer was basically trying to get constraints for the broad component found in NGC 4151, which is a Seyfert 1 galaxy. This is an image of it here on the left. And so very interestingly, if you take a spectrum of this with APO of the center at whatever position angle you want, in the red side of the spectrum, you'll get something that looks like this. So right here, what you're looking at is H alpha here in the center, and nitrogen 2 on both sides, and sulfur 2 on the left, or on the right. But what you see here in all these various different colors are independent fits to this gas. And in the very beginning when we first did this, this wasn't good. It's not supposed to look like this, because when we fit these components to the gas, we want to be able to extract the narrow emission lines from the broad. And so it's sort of a challenge to basically, as Dr. Crunch will always say, separating the chocolate from the peanut butter. And so essentially I wanted the chocolate to do narrow line kinematics with, but we needed to find a way to remove or get constraints on this broad component, because here in orange, it's just free to be whatever, and you can see that it's overestimating on the right, and it's just not good. And so we were like, great, so what do we do with, how do we get the constraints? And so we turned to our friend, the ENM spectrum, and we say, well, over here on the blue, where I pointed out in the very beginning, you have the strong O3 and H beta. And so what we essentially did was we said, hey, over here on the blue side, we have these strong O3 emission lines, which shouldn't have a broad component. But then there's H beta over here, and that is able to essentially have a broad component. And what we essentially did was modify the code just a little bit so that we could fit H beta and a broad component, which is what you see in orange laid out here. And when you do all that, you get these constraints for the broad component. Because we know the position from how far it is from this strong 5007 line, the width we found to be equivalent to this, and ultimately we wanted the height to be free as you marched along the slit. And so when you finally do that, and you go back to the red to put these constraints into the broad component, you end up with a very nice fit that looks like this. So here in the cyan color is the actual broad component with these constraints. And you could see now we have some really nice narrow emission lines, which are these guys. And the magenta gives you the total flux from all these three components. And so I always say that this is one of like my best fits I've ever made, because I've probably made thousands of fits of all this stuff. So I was very happy to see that. And so that was that. And so in summary and discussion, so we set out to calculate mass outflow rates for two galaxies, Markarian 3 and NGC 1068. We can calculate the narrow line region mass, peak outflows, and global mass outflow rates, which are essentially you take the mass that's inside the narrow line region and you average the entire velocity and divide by your farthest bin that you would go, and that's what you would get from this. And so I'd say we're just about almost there. I'd say these are preliminary mass outflow rates, but they're almost there. And secondly, we set out to get these constraints for the broad component, which we did here. And in the future, I want to be able to use these narrow emission lines that we get now from this to run disk fit models with, to get better constraints on how the kinematics is distributed in Seyfert-1 galaxies. And in summary, I just want to give a big thank you to everyone who's been involved in the team. I also want to give a big thank you to the undergraduate, everyone involved in the undergraduate research committee for awarding me the Ragwan Scholar Fellowship, and also to the man himself, Dr. Ragwan, for making it possible. Big thank you. And with that, I'll be happy to take any questions.
Questions for Francisco?
Yeah.
So do you have to worry about unseen or non-luminous dark matter mass? Also about obscuration from the torus or something?
It's a good question. Not so much. No, I mean, all we just use are the modeled values and just go from there. So I don't think the modeled.
In the
Yeah.
luminous outflow rate.
Yeah.
So not quite sure what dark matter doing so things now.
Yeah.
But we do account for red, right? So
Yes,
things
yeah.
will help us recover the truth.
That's right. Yeah. Yeah. Yeah.
So you got preliminary mass outflow rates for these two new galaxies. How do they compare to Mitch's results?
Yeah. So if you take a look at some of these, so they're awfully high, because Mitch had previously in his 3 sample had gotten like, I think the new corrected ones were like 5 or 6, 7 solar masses per year.
We did have one that we corrected. We have a Murata now, which is more like 15.
Yeah, but as I learned this morning, I found a little boo-boo in the code. So I actually have overestimated the mass from one thing that I was doing. So I expect that when I go back and make that small correction, that these will significantly drop down quite a bit and roughly be in the park of like the global outflow rate. So yeah. So they're almost there, but yeah.
You've obviously done a lot of stuff over the years, Francisco. Good to see it.
Thank you.
This is your last public chance here in Atlanta. Why in the world did you study exploding bagels instead of stars?
AGN are cool. Look, I threw this was just for you, man. This was just for you. Look, I mean, there's a star and there's a black hole. Which would you choose? Do you want to be the star or do you want to be the black hole? Yeah. So any other last questions? All right, cool. Well, thank you.
And now we're going to go from very, very big things to very, very small things with our next speaker, Brian.
Okay, so hi everyone, my name is Brian Cabau. I was working with Dr. Sidong Lei this summer. The title of my presentation is 3D lithography technology for microscale functional structures. Need this. So that's a whole mess of words, but basically we have a powerful laser and a couple of small mirrors, and we're achieving a micron scale 3D printing. So there's some important concepts to know with this project, and that's one of them being 2-photon polymerization. This is actually how we achieve a polymerized structure. So on the left you see a diagram there. You have a focused light source, in this case a laser beam, hitting a photosensitive material called a photoresist, and it's usually made up of ferric ammonium citrate or potassium ferricyanide. And that directed beam creates a polymer structure in whatever design you decide to make. So the next thing is a major hardware component. It's called a mirror galvanometer. So it's a pair of mirrors controlled by some motors independently. And there's an X and Y mirror. So if you have an XY plane, you can move along an X-axis or Y-axis with these mirrors and get across the whole sample field that you're using. So if you've ever been to like Stone Mountain light shows, they actually use a mirror galvanometer to project onto the mountainside. So what are we using this thing for? So I'm sure we're all aware of like the commercial applications of 3D printing, but for the rest of industry and academia, we can do highly precise 2D printing to create circuits. We can do things in the microfluidics field, creating microfluid channels for a biosensor, and advanced manufacturing of functional structures. So that includes building superconductors, functional ceramic, and photonic structures. I think a cool one is functional ceramic because you have, like the DoD, Department of Defense, using things like graphene and to build these complex lightweight structures for their applications on covering like tanks or whatever. So the way I like to think about that is like you ever have like a chocolate bar with a bunch of air bubbles in it? That's kind of what we're talking about. It's like a really lightweight thing. And so anything that you do with lightweight structures kind of encompasses functional ceramic. So that's a cool application. So let me get to the hardware that I'm using for this project. So first off, we've got the mirror galvanometer on the top left there. Say the X mirror is on the top and the Y mirror is on the bottom. So you can adjust the angle up to about 30 degrees, I believe, and you can reach the whole sample space of your field. That's controlled by 2 servo motors, so 1 motor per mirror, so there's 2 of them on the bottom, and you use voltage signals to direct the angle of the mirror. Our laser is a TI Sapphire, so we're working between 750 and 1200 nanometers wavelength, and the beam size is less than 5 millimeters. Lastly, we've got a DAQ card, which is a data acquisition card, and this is like the medium between the user input in the software and the lab equipment, the hardware. So you can use different waveform functions to control the motors there. So here's a diagram configuration of our setup. So I like to split this in half between the intermediate image plane. So on the right you have a basic microscope. It's got a tube lens and objective lens, and you've got your sample down here. For our purposes, it's going to be about 250 nanometers microns squared. And on the left side you have our galvo mirror setup with the 2 mirrors and also a scan lens. So the scan lens is going to trace the laser beam down to the sample, and you can put a camera sensor at the intermediate image plane in order to capture the image. Between the scan lens and the tube lens, it has a telescoping effect, which is going to focus the beam to that point on the sample plane. So there's 2 software components for this project. The first one is developing the toolpath, so like the direction, exactly what it sounds like, the path the laser beam is going to take to cover the whole surface area of the piece of material. So we're simulating it through Fusion 360, a CAM software that's computer-aided manufacturing software. And so we have a common circuit pattern there, and we want to cover the whole surface area. So what we're having is a toolpath that goes line by line here, iterating Y values as it goes up and down the X-axis. And it covers the whole surface area, and when it travels from one piece to the next, the laser is going to be shut off until it gets to that next piece. So it's just simulated using a milling tool because it gives precise measurements of X and Y values. And we want to keep those in an array, but how do we get those to our second piece of software? LabVIEW is like a graphical interface for programming lab equipment. So we want to take our toolpath file, which is a list of X and Y coordinates, and we want to store that as a 2-dimensional array in LabVIEW so it can reach all of those coordinates as it's traveling with the laser beam. There's some kind of compatibility issues with LabVIEW and other CAM softwares. Luckily, there's a JavaScript program which reads out our toolpath file to a text file, and from there we can read in. LabVIEW has a function that will read in text files, and we'll just store that as a two-dimensional array in LabVIEW. So actually moving the laser, so this is where the data acquisition card comes in. You use waveform functions to move the mirrors through the servo drivers. So there's one signal per mirror and an additional signal to control the exposure of the laser by an optical shutter. So we decided that a sawtooth function has the best pace for the movement of the laser as opposed to like a sine wave, which we found to be too slow. So there are some variables to consider, such as the mirror angle corresponding to the points on the x and y plane. There's an equation that will correspond the angle of the mirror to the corresponding location on the plane, and the time spent at each point on the sample. So how long is the laser sitting at one point on the sample space? So we'd like to move from 2D to 3D laser scanning by layering. So add a Z component and kind of just stack these things on top of each other, creating a 3D shape and structure. So once we've finished the engineering portion of this project, we'd like to move on to functional structures and circuit design. So the things I mentioned earlier, like creating superconductors and functional ceramics, those kinds of things. And that's all I have today. Thank you.
Okay, do we have any questions for Brian?
Yes.
What sort of 3D printers do you plan to use?
So it's just the hardware that we have. We have this is like pretty much everything. The only thing that's not pictured here is the laser. So everything on this slide is what we're using. Yes.
You said this was like micron resolution.
Yes.
So, Intel makes chips, which is transistors, which are 20 nanometers.
Right.
I feel like, and forgive me if I'm asking if you didn't do this at all, you may not have, but I feel like the answer to my question, which I haven't asked yet, is different materials. The question is, well, why does this matter? I mean, if you could use an SEM, you could resolve something much smaller. Is it there are a specific set of materials which certain types of photoresist just are no good for, and you want to do a completely different type of lithography, or?
That's an excellent question. I don't think we've exactly narrowed down the specific application that we're going to do. So we're just kind of working on the general software for this thing. But yeah.
To answer your question like this, so for the SEM, one thing that for the industry, no one uses SEM to produce devices, right? It's very expensive and very consumer tool. But sometimes you want to fabricate some micron size structure, especially for the biology application, right? So, but for this one, it's like polymer and the soft metal material instead of semiconductors. So SEM and the traditional lithography tools are all developed for silicon and silicon dioxide something else, right? But this kind of stuff is developed for the soft metal material, right? For example, like the maps, like the position sensor, for example, in your cell phone, or for some cell manipulation, like something like this.
Thank you. Any other questions? Yes.
You mentioned that you wanted it to not set it up so when it goes too slow, but would there be some downside to any worry about it going too fast? Like keep it as fast as possible.
We kind of want to, I think we want to push it because the only thing that would be limiting would be the hardware. And the hardware is specifically made for this purpose, so we want to push the software to its extent.
Brian again.
Thank you.
And now we will have the first of our two team presentations with Team S Phoenix. Woo!
Using a microphone if there's two of us.
Trade it off so that we can hear
Stuck
better.
on the side.
I don't know who wants to run the clicker.
First. Or you introduce yourself first. Yeah, let's start with it. Yeah.
Wait, should we stand on the same side?
Okay.
The laser.
Okay, so we're Team S Phoenix. I'm Justine Eddy.
I'm Saif Ali. Okay, so we're going to start out with the standard model. So our standard model describes 3 of the 4 fundamental forces of nature: the weak, electromagnetic, and the strong nuclear force. So the nuclear strong force, we have to consider quarks and gluons, gluons being the mediators of interaction between quarks. And what we study specifically is high-energy nuclear physics. High-energy nuclear physics studies the fundamental interactions that happen between quarks and gluons in these extreme states. Microphone. Okay, so the quark-gluon plasma is a state of the universe that existed a few millionths of a second after the Big Bang. And so at this point in time, the universe was entirely composed of this soup of quarks and gluons that hadn't formed into any other matter. And so what makes it interesting to study is that in a regular energy model, in a regular energy scale, in an everyday energy scale, the quarks and gluons are confined to hadrons, which makes them, you can't do any calculations on them. But on the energy scale at the beginning of the universe, or energy scales during heavy ion collisions, the quarks and gluons become deconfined from the hadrons and makes them measurable, and you can do experiments and calculations on them.
Okay, so basically what GSU is focusing on is the S Phoenix. It's a particle detector at the relativistic heavy ion collider at Brookhaven Lab, or we call it RIC. It's basically the successor to Phoenix at the 8 o'clock position here, and RIC. And our goal is to make precision jet measurements, and jet's just the spray of hadrons, to study energy transport properties of the quark-gluon plasma that we were previously talking about. And how we're doing that is with heavy ion collisions, and in our case we're using gold and gold collisions. So even more in focus, GSU puts their time into the HCal, which is the hadronic calorimeter, and it's currently under construction at BNL. And to show you the scope of the project, here's the little man right here. So it's really just a big project we're working on.
Okay, so the hadronic calorimeter, the HCal. So what that does is allows us to reconstruct the jets. And that is crucial for the jet energy loss studies, which teaches us about the quark-gluon plasma. And so jets are composed of hadrons, these particles that originate from these heavy ion collisions. And so the hadronic calorimeter's job is to measure these hadrons, the energy of these hadrons. And so the HCal is going to be composed of these scintillating tiles that will be sandwiched in between this steel. And so the steel thing you see here is a sector. And so each sector contains these steel absorber plates that we put the tiles in. And you're going to have 32 of these sectors that surround S Phoenix, that are sort of like a barrel formation around S Phoenix. Okay, and the scintillating HCal tiles. So they're created by a company in Russia called Uniplast. And so here we have a tile that we can show you. So the different components of the tile is that the inside.
This
yeah.
is a wrap.
There you go. Yeah. So the tile is made up of a plastic, an extruded polystyrene, polystyrene meaning just multi-structured plastic. And then you have here the wavelength shifting fiber. And this white coating here is the reflective coating, so that whenever there's light inside the tile, it doesn't bounce out. The white coating reflects the light back inside, so it stays in the tile. And so HCal, the hadron calorimeter, is going to be composed of 7,680 tiles. At GSU, we've received about 20% of them, and that was our summer task, to test and characterize the performance of 1,560 of these tiles. Okay, so more on the tiles. So these towers are consist of 5 tiles each. So we're going to be putting 2 stacks of those. So in one row here, or one column here, you have 10 tiles. The point of stacking them all, stacking 5 tiles together, is during the collisions in S-Phoenix, whenever they're detecting the particles, these 5 tiles are going to be acting as one. And so the goal was to have 5 tiles that perform in a similar way, that that light production during the scintillation process is around the same for those sets of 5 tiles. And so we have to do that for 12 different tile shapes. So here you have a drawing of what the tiles will look like whenever they're in the tower. So if you flip this way and turn it so you'll see you'll have the tiles going flat this way. So this is like a top view, a top cross-section view of the sector. And so here you have 12 different tile shapes. This one, being very wonky looking, is the one at the very end, tile B32, so we have 21 through 32. Okay, so before we start testing the tiles, we have to do a few things to them. So one is that the tiles are designed to be 8 millimeters thick, but the steel absorber plates have a 9 millimeter gap in them. And so we have to test the thickness of the tiles, because the tiles, along with the plastic, also involve the wrappings. And so we have to test those to make sure that they fit between our gauge. We have a tester gauge here. And so if the tile had difficulty going through the gauge, we would mark it. We would send it to Brookhaven National Lab, where it's being built, S-Phoenix, and they would test that tile to make sure that it would fit into the steel absorber plates. And so we are the ones who are responsible for making sure that they know which tiles they have to look out for. And this is an example of a tile inside the plate, so it's very tight fit. Another thing we had to do is ensure the tiles fit inside the detector longitudinally. And so here you have a drawing, and here's the actual device we used. It's the dimension tester. And you have these different pegs that correspond to different tile shapes. And so what we would do is we would put these metal pegs inside those holes and test the shape of the tile, because there's only a certain amount of clearance that the tile has, because they need to be able to fit across the sector in a very particular way. And so we had to test those dimensions to make sure that that would be good to go whenever tiles went from GSU to BNL. Okay, so performance characterization, which was our whole job for the summer. The way this worked is a test stand that was designed at GSU. And so the process is you have a cosmic ray that strikes the tile. And then the tile scintillates, produces light. That light travels through the fiber, wavelength shifting fiber, out to an SIPM, silicon photomultiplier, right here. And then from the silicon photomultiplier, that signal goes out to a Kane unit. So that signal from the silicon photomultiplier is an analog signal. But what the Kane unit does is it converts it to a digital signal so that the computer can read it and plot it out. And so what happens is on the x-axis we see the ADC value, the analog to digital conversion, that the Kane unit is responsible for right here. And on the y-axis you have the count. So the peak location of the ADC value right here, we say is our most probable value. And that MPV is our proxy for the performance of each tile. And so our summer was testing all 1,560 tiles so that we have an MPV of every single tile that we can use for performance characterization.
Sorry. Okay, so, okay, so this is an example of what a test output would look like. So right here at the top, we have a top reference tile, and down here is a bottom reference tile. And the 8 in between are 8 corresponding Landau distributions for the 8 other channels in the test stand. So Saif talked a little bit about how we get the MPV value. So we take that MPV value for each of the 8 channels that aren't the reference tiles, and we divide it by the average between the top and bottom reference tiles. That becomes our performance ratio, and that's how we characterize the tile and its performance. And that's how we turn it or put it into the towers. So we grab 5 tiles that behave similarly with a similar performance ratio, and we put them together. And then they behave as one. So this is a global distribution for the PR values. So that means that this is all of the tiles we tested and their corresponding PR value. And as you can see, it's peaked at around 1. But what we're looking for is just for it to be close together, so we can have ample amounts of PR values that are similar to group together. You can also see here is 0.8. That was our cutoff for PR values that were a low light yield, so they became our bad tiles. We even had a little bad boy tile shelf. So those only accounted for about 29 of the approximate 1,500 we tested, so 1.9%, and so we considered that also a success.
Are you keeping the high performance tiles?
Yes, sir. We actually did tests on that.
And does that introduce any sort of bias?
So initially, our range was 0.8 to 1.2. Because the 1.2 performance ratio tiles mean they have a higher light yield than the reference tiles, but then we figured out that there's nothing necessarily bad with that. But we did have like a few tiles that are way, way out here, and those we kept because we weren't quite sure what happens whenever you saturate the SIPM with that high of a light yield that comes from the tile. So that's something we're still not quite sure on. But yeah, it was a problem that we ran into.
But yeah, originally it was 1.2 was the cutoff, but as we actually, we did notice, that's kind of goes in the next point actually. When you look at V24s and the PR values for each individual tile, as we get later shipments of tiles, we noticed that the PR value was increasing as we got later shipments. So we got shipments from January to May, and as time went on, you can see a similar peak to the one that I showed you on the global distribution at around 1, but then one that's later at around 1.3 that you can mostly see on tile shapes that we received in later shipments and over time. So that led us to the question, is there a change in production and what was going on? So we actually decided to split up the PR graph for the different tile shapes. As you can see here, the first peak correlates to shipment 1, and the second peak was shipment 3. So we could clearly see that there was an effect over time, that there was higher PR values with later shipments. So that made us come up with the hypothesis that, wow, they must have changed something at Uniplast, our production, our producer of tiles. And so we actually had a couple team members go to Russia and Uniplast and see what was up. And we were confirmed that they had actually changed how they put the wavelength shifting fiber into the tile. They became more just better at doing it, which allowed us to have a higher PR value. And so basically what that helped us figure out was that our way of measuring the PR value actually gives us information on the actual how the tiles perform, because we knew that there was something up with the production of the tiles before we even knew that it existed, basically. So there's also the boxing and the shipping of tiles for B&L. You can see Saif here in his little squat position. When we were done testing tiles, we had to pack them up and send them back to B&L, which is also some physical labor that we had to do over the summer. But yeah, as soon as we tested them and put information into the database on the PR and MPB, we sent them to Brookhaven, and they were able to access that information and have the tiles with it. So in conclusion, we've tested 1,506 tiles out of the 1,560 tiles that were sent to us. 12 of those, not included, are reference tiles. We also had enough to fill up 6 sectors, as Saif was pointing out the sectors before, to fill 6 sectors, and that was a huge success for GSU and BNL, which gives us confirmation basically that we'll be successful in the assembly stage and also the full production stage as we keep on testing tiles and sending them to Brookhaven. And also you can see here, this is our team. You can see all these boxes, they went all the way down the hallway. And they're all gone now. This is actually not our stuff, so all clear. Until we get more tiles, which is pretty soon, so then we'll have to switch the pictures back.
Okay. And so what's next is, now we're just doing ongoing analyses on the data that we gathered over the summer, different diagnostic tests, and just different analyses and stuff like that. And we have some leftover tiles, so we're just running more tests while we have them to see if there's anything new that we can find out, and gearing up for full production. And at BNL, assembly of the towers has begun. You can see our own Dr. Connors helping with putting the tiles in. And so that's starting to go now. You can see the tiles here too. So those are the ones that we test at GSU that they're putting in the towers now.
So that's basically it. If you guys have any questions for us, we're happy to answer them, if we can.
Yes.
This is purely a curiosity. You said you were responsible for 20% of the total number of tiles that we used in this experiment. Is that including the ones that are coming in, or you got even more than that you're responsible for?
Right, so 20% is considered the pre-production, and so those are incoming. The rest of them are coming in soon. So yeah, so that was only, so the whole summer's worth of work was only 20% of the tiles. Okay. Yeah. So there's a lot of work to be done. It's going to take a long time. There's going to be many more summers. Hopefully not too many more summers, but at least one more summer. Yes. The wavelength shifting fiber? Right. So whenever a cosmic ray or high energy particle strikes the tile will scintillate light. And so that light inside the tile is moved to the wavelength shifting fiber. And so that fiber is responsible for finding the shortest path for routing that light to the SIPM, or out to the fiber outlet, which will have an SIPM connected to it. And so that SIPM is what will help us have some readings and data. Yes?
So it sounds like you got shipment 1, 2, 3, 4, and you tested them sequentially. Did you at any point go back and retest section 1 to make sure your measuring technique wasn't drifting instead of the actual lines themselves?
Mm-hmm.
Yeah.
Yeah, occasionally we had, specifically when we were seeing the high PR values as they increased, we would get some wacky ones like we had never seen before that, because as we previously determined before we were getting those high PRs, they're around 1.2. So whatever we would have in store, we would try to compare it back as we were seeing higher values. And that's what helped us come up with the hypothesis that something was up.
But generally, we didn't necessarily test shipment 1 tiles, and then 2, and then 3, and then 4. We got all of the tiles before our summer work started, I'm pretty sure. And so we kind of just picked up the box, unwrapped it, and tested it. And then made the plots after, or as we went along whenever we started noticing this.
So if you tested one tile 5 times, what's the error bar on the measurement?
So that's something that we're doing, that's something that we're analyzing now. We're noticing there isn't much change whenever you don't change the channel number, the order in which the tile was tested in. So you have a stack of 8 tiles that are going to be tested at once with 2 reference tiles, one on top and bottom. If one tile is on channel 4, and you test it and retest it again in channel 4, there isn't much of a change in performance ratio. But if you change the channel, we're noticing a little bit more change than we'd like to see from different SIPMs, so that's something that we're studying.
Yeah, it's complex enough you won't get bored.
And this summer's program was a multi-institutional program, and Zoha is visiting us from Georgia Tech. Yes,
Can I stand on the other side? Does it matter?
Hi.
Hi, my name is Zoha, and I'm a biophysics student at Georgia Tech, currently interning with Dr. Damla for the summer. And I have been working on a project that deals with a spectral analysis toolkit with applications to functional connectivity of the brain from EEG and fMRI data. Okay, so first of all, I'm working at the neurophysics lab with Dr. Damla, and what is neurophysics, since I'm the only neurophysics person here, and only biophysics person here also? So neurophysics is a subdivision of biophysics, which just basically is looking at biological or the nervous system from a set of physical principles. So we're understanding it with more technical ways. So this is actually a humongous field. It includes dynamical systems, information theory, neuromechanics. There's a lot of applications. Specifically at this group here at Georgia State, they focus on neuroimaging, both functional and structural. Functional neuroimaging is focused on understanding what parts of the brain are working in what ways, like what do they do, how are they working. Structural is just understanding how they're shaped, how they look. So the two main types of data sets that we're acquiring are the most common ones in neuroscience, so fMRI and EEG. So they're both time series data, and fMRI is functional magnetic resonance imaging, and it's just basically still using an MRI machine, but we're looking at blood oxygenation level changes to qualify neuron activation. Because when your neurons are firing, your blood is also going to be rushing to that area of the brain to activate it. EEG data is electroencephalograms, and it is you put electrodes on your brain and just measuring outside electrical activity changes. So they're both non-invasive data, and that explains why they're the most commonly used in neuroscience. So other things that we use with this data in accordance is computational modeling for understanding how the brain is working, and so we can predict things in the future, and just analyzing. So as you can see from my title, I'm going to be talking about spectral analysis a lot. So it's basically used in many fields. So it's interpreting complicated signals. So there's three main categories, I would say. One is the Fourier transform, which is just deconstructing a signal into multiple sinusoidal functions. The wavelet transform, which is just a different type of function that decays from the origin and is also a square integrable. There isn't really much more to say about that. And the time-windowed Fourier transform. So wavelet and time-windowed is meant for a non-stationary signal that can change greatly over time, while Fourier doesn't necessarily look at that. Okay, so I just talked about this data, but how does this look like in a simulated example, or like how does it look like in neuroscience, like using it? So I will be working through simulated data and trying to understand, like see how we interpret it using these analyses. So the data, since it's simulated data, we know what it's talking about. So we're going to look at a three-channel autoregressive, a three-channel time series data created from an autoregressive process. We already know, based off of this is the three channels that are visualized. You can relate them to a brain channel or different electrodes. So we're going to be looking at Y, X, and Z. So what we know, because it's a simulation, is that they're all related to each other, but they're different driving processes. As you can see, Y, I should just do this. Okay, Y is driving Z, while Z is driving X. However, X is not driving anything. There's no arrow coming away from X. Also, Y, because it is driving Z, which drives X, is indirectly driving X. So we know this, but hypothetically, neuroscience, we're trying to take these time series data to try to understand this. We don't know this. So let's see how these spectral analysis tools actually gives us the same conclusion. So the first question that we're kind of looking at is, are there any oscillatory processes or oscillations in our signal? So that is showed to us by looking at the power, which is one of the three main spectral quantities we're looking at. So we can see that all three channels are spiking at 40 hertz. So yes, the answer is yes, there is an oscillation. But power literally only tells us the relative strengths. Does it tell us how these channels are related? Does it tell us what is doing which part, or what is more important in understanding this brain process? No. It is literally only showing us the relative strengths. So now we're asking, how are these channels related? How are these electrodes or brain regions related? So that is coherence. Coherence looks at that. So coherence is not a directional quantity. We're only looking at it, how related they are. So I only have 3 graphs for each of the different combinations. So as you can see, they all have non-zero coherence. They're all kind of relatively similar. So we know that they're all related somehow, but what's driving what is more important in potentially modeling this brain or this task that we're looking at in neuro. And we will come back to this, but this is just going over that. You can see that there's indirect effects. So the last and most important thing that is heavily focused on in our lab is Granger causality, because it is very important in modeling. Basically, Granger causality is asking, if we are trying to look at a model of multiple processes, is the model a better fit if we add this process or not, this channel or not? So if the model, if we include multiple channels and the model is better to the data, then that's what Granger causality is saying, that this is more important. But if the model doesn't change, or isn't fitting the data better, then there is not much causality. So causality is bidirectional. So we have to look at it from both sides of the channels. So I plotted all of these according to their reverses to show the huge difference. So for X and Y channels, you can see that Y had caused the process in X, but as you can see, X does not affect Y. It's 0, a stark difference. And that's the same case, there's a similar case for XZ and ZY. As you can see, X, once again, does not drive any process, while Z does. And the same case is over here, where Y does not drive Z, but Z does drive Y. So, but you can see that they have very similar amplitudes. However, they're still very different because it's causality overall, which is why I was talking about the conditional causality. As we can see, Y only conditionally drives X. And if you look at the YX plot, it is somewhat smaller than the rest if you look at the scale. So that's another thing that can be further explored as we look at the modeling. So this summer, I have been working on making a graphical user interface to create a very easy to use program that is for neuroscience use that we can put in all of these spectral analyses. So a lot of neuroscientists aren't very technically trained, so this is important for them because we want more data. That's really good for neuro. So the first part of this GUI is pre-processing data. That's where you just load data that they already have, experimental data. And also, if we need to filter it, if they have noisy data, if they haven't already done that, it's all here. The second part, choose between the second and third part based off of what you want from your data and what kind of data you have. So the second part is basic for indirect Fourier transforms and autoregressive models. So this is basically looking if you want to implement those methods on your data. They can be both EEG, fMRI, doesn't matter. And the third one is wavelet analysis. So wavelet's really good at looking at non-stationary signals. And once again, we want it to be very easy to use. So we have all three of the spectral quantities and different ways to graph them. So this is all in MATLAB, if I haven't already mentioned that. Fun. So basically, we're acquiring all this data for neuroimaging. What does it do? What is important? Well, basically, we're trying to model the brain. The brain is very important in every single human, essentially. So there's lots of disorders and issues that occur that we need models for. Because neurosurgeons only know how to cut the brain. They don't really know what's going on as much in the physical. So going into cutting the brain, let's talk about Brodmann area. So this is one of the most, it's one of the most common ways to organize the brain. It's pretty old though. It's not very functionally oriented. So yes, basically a neurosurgeon was like, let me just cut up the brain and look at it under a microscope and be like, these cells look different. I'm going to name it 1 versus 2 versus 3. But does that really give us any information about what that area of the brain is doing? Not quite. So because of these functional imaging, we start understanding how to better models for like tasks such as vision, decision making, etc. So we are trying to chew this and do better. So Granger causality is directly correlated, creates like linear prediction models. So specifically for the brain, like I was saying earlier, we're looking at understanding certain processes. So we want to know for sure which part of the brain is more important for a certain process. Like remember, the neurosurgeon is just going to be listening to us and be like, what part am I allowed to cut out again? So we're going to need to do that. So the causality will tell us what is the most important part of the brain process, what is more important for modeling and understanding it. So the neural field theory and equations is just essentially is another way of modeling it. So we're looking at neural networks, we're looking at different channels and regions. So it just describes this system into multiple variables like firing rate, synaptic activities, and just describing it into different regions. And essentially, that is all. I wanted to just acknowledge the group I'm working with and the internship program, which has been a great help in mentorship this summer.
Any questions? Brain talks.
Yeah, the only neurophysics person.
Oh, you got one!
I actually have so many questions.
Oh my gosh.
I just want to check my understanding, make sure
Yeah.
I understood, because it felt like there were two sections that taught me justification.
Of course, any question.
Is the purpose of creating these causality models to think of the mapping of the functionality of the brain in a very, very general sense, to say I have a region X and a region Y?
I wouldn't say that's general.
How do they play together? Is that why you went through the whole business of saying what is the causality relationship between X, Y, and Z?
I feel like this is a yes or no question. I think it's a yes. I don't know. I would say yes. But like the whole entire point of those causality things is understanding the relationship between different parts of the brain, because otherwise we have no way to qualify what that part of the brain is doing and how it's affecting another part. So that's just our way of qualifying those processes.
So do you have so I've been, when I brought to like a new topic or something,
Of course.
I have like professors be like, draw a cartoon picture for me, Do you have like a simple, like this is an example of an X, this is an example of Y, or this is a Z, or is it just there's just so many different things that you guys try to dissociate yourself from that?
Are you talking about brain regions like X, Y, Z?
No, not spatial. I mean the functional relationships that you're talking about in the first half of the talk.
Okay. Is there a particular slide?
This model. Right?
Okay.
You have this very abstract notion of X, Y, and Z. Can you give me like an example?
Okay,
of
well,
what X might be?
of course. Like I said, a brain channel or like electrode, because electrodes. I don't know if you're aware. It's just you literally choose where to put them on. So you try to map it with where anatomically, like what area of the brain you're looking at. It's literally you pick which electrode goes where. So these would just be like the electrodes we're recording data from, because like obviously not every experiment is going to record data from every single part of your brain. Does that make sense?
So all three of these would be different regions you were programming, and you're just looking for the.
Yeah. So this I was saying earlier when I was going over. I'm sorry if I said it quickly, but it's basically these 3 channels are going to go over where we're recording from, whatever you want to quantify that as.
Really cleared up for me. I don't know.
Yeah. No. Of course. I'm sorry.
Oh, you got one more.
Can you go back to your brain model?
Wait, like.
The one where we see the colors.
Okay, Brodmann's areas, yes.
Something that's been bothering me whenever I look at those things.
Yeah.
So you're assuming that the brain is like a surface, right? Because you're placing electrodes on it?
Yes.
But it's a rippled surface because of the tensions, because basically our brain is too large to fit in the cranium, so it ripples itself. So how do we get more resolution, or how can we get data for the part of the brain that's in the ripples, that is folded on the inside?
inside.
It seems like we have a good angle on the outside, but how do we
Okay.
get on the inside?
So neurosurgery. So there actually are some. There actually. No, I don't know if there's a non-invasive. Does
Placing the electrodes that you can get more resolution on the parts that, because it's not like a flat surface and you just dump electrodes on it on the surface, but is it?
a non-invasive method specifically, you're asking?
Yeah, is there a
Sushma, do you have any idea about?
So you need to get these images, right?
Well, these images are probably a model, but you see how it ripples and there are sections that are folded on the inside that are sort of in between, right?
He's asking about the technology available.
How can you get data?
I'm not sure.
So what we do is we take the image and slide it from 3D and combine them together to get the 3D.
With electrodes on the surface?
Not with electrode, MRI, so that's what the.
Oh, with the MRI, okay.
Okay, that's the answer. We just MRI. Is there some technology I'm not aware about? I haven't done any experimental work. I'm not sure.
MRI. And yeah, basically, it's not the oxygen, but the decaying of the hydrogen atoms.
Well, which is in the oxygen, but whatever.
So you have to go to
Let's thank so.
Sorry I couldn't answer that directly. I haven't done any experimental work this summer, so I haven't really thought about that. I've just been coding GUIs.
There's a book I'm reading that talks about how the brain works, and he talks about this technique being equivalent to putting microphones outside of baseballs.
Yeah.
Got it.
Yeah, I went to a talk where they were so happy that they had neurosurgeons implement electrodes, and they're like, yes, this is beautiful data.
Is that being done? So question for you, is that being done actually implanting electrodes on the inside, like tiny electrodes?
Yeah, but that's only special cases. I feel like not many people want
Are you volunteering?
I mean, for sure, there's extreme cases, people who are having seizures, extreme seizures, that they can't function normally in life. They're going to want to go to the extreme method and have electrodes implemented. Yeah.
That's the only way.
Yeah. But it's that's an experimental questions and experimental biophysics or experimental physics in general. And so there's a lot that we can't control. We're working on experimental design for it.
I think so. And I didn't put it in the program because it didn't fit aesthetically. But let's go ahead and take a 5-minute break, and then we'll start with the second half of presentations. There's still snacks and drinks, so please help yourself, and we will reconvene in 5 minutes.